This paper presents SiMWiSense, a novel framework for simultaneous multi-subject activity classification through Wi-Fi signals. The framework addresses two key challenges: scalability and generalization. Scalability is addressed by utilizing multiple Wi-Fi devices as channel state information (CSI) collectors, where the closest device to a given subject is used for classification. Generalization is addressed by developing a brand new few-shot learning algorithm called Feature Reusable Embedding Learning (FREL). The paper first introduces the concept of Wi-Fi sensing, which leverages tiny changes in the CSI to detect physical changes in the environment. The authors propose using multiple CSI collectors to capture the independent propagation path between the corresponding antenna pair of the access point, AP, and the device. They experimentally prove that the device closest to the subject dominantly characterizes the channel property between itself and the source of the Wi-Fi signal. The sensing proximity test is performed in 3 different environments with 3 subjects and 20 activities. The results show that the CSI monitor closest to the subject performs better than other CSI monitors. The accuracy of subject 1 is 95% from the CSI data of monitor 1. Whereas the accuracy of subject 2 and subject 3 decreases by 30% on average with monitor 1. However, their performances improve drastically to 96% and 97% when considering CSI monitor 2 and CSI monitor 3 for subject 2 and subject 3, respectively. The SiMWiSense framework consists of 3 main task blocks: sensing, preprocessing, and learning. The sensing block captures the CSI data. The preprocessing block extracts features from the CSI data, and the learning block uses the FREL algorithm to classify the activities. The FREL algorithm combines both embedding learning and metalearning approaches to achieve better performance through fine-tuning the classifier with only a few additional samples. The paper presents an extensive data collection campaign in 3 different environments and with 3 subjects performing 20 different activities simultaneously. The results demonstrate that SiMWiSense achieves classification accuracy of up to 98%, while FREL improves the accuracy by 85% in comparison to a traditional convolutional neural network (CNN), and up to 30% when compared to the state-of-the-art few-shot embedding learning (FSEL), by using only 15 seconds of additional data for each class. In the context of multi-subject detection, a decentralized sensing system named SiMWiSense is proposed, which utilizes a novel Feature Reusable Embedding Learning (FREL) algorithm to adapt to new scenarios with only a few data samples. The system's sensing and preprocessing blocks collect and process Wi-Fi channel state information (CSI) from multiple devices. The FREL model consists of an embedding network and a classifier, trained jointly during the metalearning phase, and fine-tuned on a small portion of data for better adaptation to new tasks. The model can be applied not just for Wi-Fi sensing but also for other few-shot learning purposes. The cascaded learning block uses a 2-stage detection approach, first identifying subjects coarsely and then determining their activities in a fine-grained manner. This design reduces complexity and enhances flexibility in a dynamic system. The paper presents a novel system called SiMWiSense, which utilizes Wi-Fi signals to detect and classify human activities in real time. This system operates in 2 stages. First, it identifies the subject, and then it classifies the activity performed by the subject. The system uses a convolutional neural network, CNN, as the baseline model for both stages. The authors also introduce a new Feature Reusable Embedding Learning (FREL) strategy that enhances the generalization capability of the model. The experimental setup includes 3 environments: classroom, office, and kitchen, with 3 subjects performing 20 different activities. 3 separate models are trained for each monitor with data collected from each corresponding subject performing activities while the other subjects perform random activities. The authors evaluate the simultaneous multi-subject activity classification performance of SiMWiSense with the baseline CNN and find that the average accuracy in the environments is high, ranging from 97.37% to 98.51%. The performance discrepancy of monitors M1, M2, and M3 is less than 2%, achieving an average accuracy of 98.0%, 96.84%, and 98.54% respectively. The authors also study the trade-off of the subcarrier resolution and the SiMWiSense performance. They find that the system performs worse with lower subcarrier resolutions, but the extensive feature extraction techniques or higher sampling frequency can compensate for this, albeit at the cost of increased computation burden. The paper demonstrates the effectiveness of the FREL strategy in enhancing the generalization capability of the model, especially when dealing with new tasks that the model has never seen before. The performance of SiMWiSense, a Wi-Fi sensing system, is evaluated in 3 different environments: classroom, office, and kitchen. The results show that the system achieves an average accuracy of 98.66% with 242 subcarriers, but the accuracy decreases to 84.92% and 62.76% when the number of subcarriers is reduced to 80 and 20, respectively. The confusion matrices of the baseline CNN model reveal that the top 3 classes that are hardest to distinguish at lower subcarrier resolutions are washhands, rotate, and brush. The performance of SiMWiSense with FREL, few-shot representation learning, is also evaluated, and the results show that FREL excels in generalizing to new environments and subjects. The overall performance of SiMWiSense with FREL in new untrained environments improves by 86.06%, 87.56%, and 86.90% when the embedding network is trained in classroom, office, and kitchen, respectively. FREL also surpasses FSEL, few-shot learning, by 25.71%, 17.43%, and 15.56% in the same environments. The confusion matrices of FREL and FSEL reveal that FREL achieves higher accuracy and is more robust in distinguishing activities. FREL can also generalize subject identification in new untrained environments, achieving an accuracy of up to 96.53%. Whereas the traditional CNN limits to 6.19%. FREL demonstrates an accuracy boost of 17.79%, 17.93%, and 17.55% in classroom, office, and kitchen, respectively, compared to FSEL. Furthermore, FREL can generalize the monitors across the environment, achieving an average accuracy of 91.71%, 94.51%, and 94.78% in generalizing the other monitors while trained with Monitor 1, Monitor 2, and Monitor 3, respectively. This enables any system to be trained only on one monitor and deployed with n number of monitors with only 15 new data samples from each monitor. The results demonstrate the robustness, reliability, and strong adaptive capability of FREL to new environments and subjects. The proposed FREL model can be used for simultaneous activity sensing and subject identification in various environments, with high accuracy and minimal training data. The proposed framework, SiMWiSense, is a pioneering effort in simultaneous multi-subject Wi-Fi sensing. It leverages channel state information, CSI, to classify human activities in a device-free and location-independent manner. The authors highlight the limitations of existing approaches, which are primarily designed for single-subject scenarios, and emphasize the need for a more comprehensive and robust system. SiMWiSense employs a fast adaptation reliability evaluation learning (FREL) algorithm, which enables the system to adapt to changing data distributions and generalize to new environments and subjects with only a few samples of new data. The algorithm's performance is evaluated in 3 different scenarios: classroom, office, and kitchen, with 3 subjects performing 20 activities simultaneously. The authors provide a comprehensive review of related work in Wi-Fi sensing, highlighting the advantages and limitations of various approaches, including RSSI-based, PWR-BASED, and CSI-based methods. They also discuss the applications of deep learning in CSI-based Wi-Fi sensing, including human activity classification, gesture recognition, health monitoring, and indoor localization. The proposed FREL algorithm is compared to traditional CNN-based approaches and state-of-the-art few-shot learning models, demonstrating an accuracy of up to 98.94% and surpassing existing methods by 85% and 20%, respectively. The authors also provide a thorough analysis of the system's performance in different scenarios, highlighting its robustness and adaptability. The paper concludes by discussing the significance of SiMWiSense in enabling device-free and location-independent human activity recognition, with potential applications in various fields, including healthcare, smart homes, and surveillance. The authors also acknowledge the limitations of their approach and suggest directions for future research.